2.5, proving segment relationships. First, we have the segment addition postulate, and what this means is that if I add two segments together, they make up a larger segment. So if I were to add segment AB to segment BC, it would make the entire segment AC. The definition of a midpoint is that it cuts really a segment in half. So if M is the midpoint of AB, then we can say that AM is equal to MB, that those two smaller segments are equal. The midpoint theorem is almost exactly the same, it just allows us to use congruent instead of equal. And then the definition of a bisector. So we can have a line bisect a segment, and it does that, and when it does that, it creates two equal portions. So if line AB bisects segment EF at point C, then EC and CF can be said to be equal. We can use these four options: segment addition postulate, definition of midpoint theorem, and definition of a bisector to help us prove things to be true. We also can use our reflexive, symmetric, and transitive properties from the other day, but now we can use them with segments, or, well, with segments. So we can say if we're using the reflexive property, we would just write the same thing twice. If we're using the symmetric property, we're reversing the order. So AB is congruent to CD, then I can flip it around and say CD is congruent to AB. Lastly, if I have two statements that are congruent, then I can say that they are congruent to each other. So AB is congruent to CD, CD is congruent to EF. Since both of these things are congruent to CD, then I can say that AB is congruent to EF. All three of them are then congruent. Okay. Sorry. All right, so example 1, we are given that CE and FE are congruent to each other. So that is CE and FE are congruent to each other. So we're going to put a tick mark for each of those. We also know that ED and EG are congruent to each other. ED and EG. So even though it doesn't appear that way, they are saying that they are congruent. Okay, so we want to prove that CD is congruent to FG. So first, our first statement is really just the given, so nothing special there. Our reason is that we're allowed to say it because it is given, right? We're just using that first statement from right there. We are switching congruent to equals. When I switch between congruent and equals, but I'm saying the same exact thing, that is our definition of congruence. Okay. Next, I'm going to say that segment CD, let's look at our segments again. Segment CD, this one on the diagonal, is made up of adding CE and ED together, and that's correct. That's just by adding the blue and the green together. Segment FG, again, I'm adding the blue and the green together, so FE plus EG. When I am adding smaller segments to make a larger segment, that is segment addition. Segment addition postulate, but we're not going to write the whole thing. Okay. In step 4, it says that CD is equal to FE plus EG, and all we are doing here is replacing. So since I know that CD is equal to CE plus ED, I'm going to replace CE with what it's equal to. So that was this replacement right here. And I'm going to replace ED with what it's equal to, and that's this replacement right here. So when I replace, that is substitution. Okay. The next thing I'm saying is that CD is equal to FG. Well, we know that FE plus EG is equal to FG. So again, I am substituting. I've replaced that expression with an equivalent expression. Since they are equal, I can say they are congruent by definition of congruence. And that is what the question asked us to prove. For the next one, we are given that JL and KM are congruent. JL is from here to here, and KM is from here to here, and we are saying that they are congruent. What we want to prove is that JK, here to here, is congruent to LM. All right, well, let's see what we can do. So obviously, we're given the given in the very first portion. It's the same thing written twice, so we write given. you're always going to put given as your first option. We're switching from congruent to equals, so that is definition of congruence. The next thing we are doing is switching, we're using segment addition here. We're saying that all of that JL is made up by adding the two smaller portions, JK plus KL, and all of KM is made up by adding the two smaller portions, KL plus KM. So that is going to be segment addition. Okay. So I have that JK plus KL is equal to KL plus LM. I can do that by really substituting. So really I'm using this concept, but I am going to put, instead of JL, I'm putting what it's equal to. And instead of putting KM, I'm putting what it's equal to. Okay, so that is my JK plus KL is going to be equal to KL plus LM. And that is just substitution. I am just replacing with statements I have already said are true. All right, the next one, it looks like we have subtracted KL from both sides. When I'm subtracting, that is literally just subtraction. You could technically say the subtraction property of equality, but subtraction's good enough. When we are left with and clean up, we get equals JK plus L, or is equal to LM. And when we do that, really we've just substituted with an equivalent expression. So anytime we're just cleaning up, that's substitution. Last but not least, we are going to switch equals to congruent, so that is our definition of congruence. The next one, we are given that C is the midpoint of AE. C is the midpoint of BD, and AE is going to be congruent to BD. So the first thing is given, that's all the information from that first statement. Next, we're saying that AC is equal to CE, and BC is equal to CD. So we have AC and CE, and we have BC and CD, and that is because C is the midpoint of both of those lines. So because we're using equals, we'll use definition of midpoint. If we had said congruent, we would have used midpoint theorem. All right, so now what we're going to say is that AE is equal to BD, and that's just taking this statement and making it into an equal sign. So that's definition of congruence. Okay. In the next portion, it says that AE is equal to AC plus CE. That's segment addition. And then BD, same concept, is made up of BC plus CD. Same exact thing, we're still using segment addition. The next says that AC plus CE is equal to BC plus BD. Well, I knew that these two were equal by this statement, so all I'm doing is replacing them. I know that AE is equal to AC plus CE, and I know that BD is equal to BC plus plus CD. So I can set them equal to each other, and that's just substitution. Okay. From there, I can also substitute again. I know that AC is, I know that AC, I know that AC is equal to CE, so I'm going to replace CE with AC. And I know that, what's another color I haven't really used? Kind of using all of them. I know that BC is equal to CD, so I can replace CD. Or, well, all right, it doesn't really matter. They're replacing BC with CD. Okay, so now I have 2 and 2, right? There's 2 of them, so when I add together, I get 2. So when I replace that substitution, even though I'm adding together, I'm still substituting. I haven't added anything to both sides. I'm just combining. Now I'm going to divide by 2 to make it disappear, so that's division. I've cleaned up, so that is substitution. And I've turned equals into congruent, so that is definition of congruent. Okay, last but not least, we have the shape, and we know that VZ is congruent to VY. Okay, we also know that WY is congruent to XZ. And we want to prove that VW is congruent to VX. So of course our first piece of information is our given. And we're switching all of those equals to congruence. So that's just definition of congruence. Okay. We know that VZ is equal to VX plus XZ. That's segment addition. And we can use the same logic for VY. That's VW plus WY. Then using substitution, we are going to do some replacement here. So we know that VZ is equal to VY. So I am going to substitute, instead of VZ, I'm going to put VX plus XZ. And instead of VY, I'll put VW plus WY. So that is substitution. Okay. Oops, I do apologize. That should be an X there, right? This is X, so this is X. So I have that WY is equal to XZ, so I'm going to replace XZ with WY. Okay, so the next thing I can do, since that was substitution, is I want to remove that WY that's on both sides. So I'm going to do that by subtraction. Okay. And then from there, I'm just going to simplify, so that is substitution. I'm going to switch the order. So when I switch order, that is going to be symmetric. Just putting the equals on the opposite sides. And then I'm going to switch equals to congruence, so that is definition